Good day, we're the group Mythical Glory, and for our project, we're going to present a machine learning pipeline of a heart attack risk model. And to start things off, we're gonna talk about the problem and then the data collection.
In this project, we frame the heart attack prediction task as a binary classification problem. The dataset provides a target variable labeled output, where a value of 1 signifies that a person is at risk of a heart attack and 0 indicates no risk. Our objective is to train a machine learning model that can predict this outcome based on a range of input features. These include medical indicators like cholesterol levels, resting and maximum heart rates, and systolic blood pressure, as well as lifestyle factors such as age and gender. By successfully identifying at-risk individuals, the model could serve as a useful tool in preventive cardiology, enabling earlier diagnosis and intervention. So for our data collection, we used a synthetic dataset available on Kaggle that's designed to resemble real-world clinical data on heart disease. Although it doesn't come from actual patients, the dataset closely follows patterns observed in medical studies and includes features like age, cholesterol, resting blood pressure, and exercise habits. And this makes it ideal for educational and prototyping purposes, especially when dealing with sensitive health information. Using synthetic data allows us to experiment and build models responsibly without risking patient privacy while still gaining meaningful insights into how heart attack risks might be predicted using machine learning. Let's begin with understanding the raw data and the assumptions we made before cleaning. The dataset includes columns like blood pressure in a systolic or diastolic format, which we assumed would need to be split for meaningful analysis. The sex column is categorical and needed encoding. We also assumed that ID columns and location-based columns like country and continent would not contribute significantly to the prediction. Finally, we prepared for possible outliers in health-related variables such as triglycerides or cholesterol, which could impact model performance if left untreated. We then began cleaning and transforming the data. First, we split the blood pressure string into two numeric columns, systolic and diastolic. We also encoded sex column to be binary, 1 for male and 0 for female. Next, we dropped unnecessary columns such as patient ID, country, continent, hemisphere, and the original blood pressure string. This step made the dataset leaner and more suitable for analysis and machine learning pipelines. To structure our pre-processing pipeline further, we categorized our features. Numeric columns included health metrics like age, BMI, cholesterol, and blood pressure components. Categorical columns included lifestyle-related risk factors such as smoking, obesity, diet, and medication use. This step was essential because the type of feature affects how we handle and model the data later on, especially in encoding, correlation, and visualization.
Alright, so for our EDA, the first thing that we did were box plots, and from this we see that triglycerides has the highest spread and cholesterol also shows some extreme cases, and we knew that we were going to use min-max scaling from this box plot, and we would also use balanced class weights to ensure neither model overfits to those rare high value points. And then for categorical association with target, which is the Kramer's V heat map, we observe that diabetes, alcohol consumption, and obesity show the strongest but still modest associations with heart attack risk, and smoking, family history, and medication use hover very close to 0 in this view. So with that, we know that for the models, we're going to keep all these predictors, and our logistic regressions L2 penalty will shrink any truly noisy coefficients towards 0, and random forest will naturally ignore splits on the weakest signals, and we'll continue to leverage balanced class weights. And for the next visualization, we also use the heat map, but this one is called the Pearson's correlation, and we observe that cholesterol and systolic BP lead the pack, and triglycerides follow, while diastolic BP actually dips slightly negative, and age, BMI, and heart rates at near 0 correlation. So what we will do for the models is that we're going to min-max scale all numeric features so that logistic regression can fit stable, comparable coefficients, and random forest can find its own linear splits without worrying about scale. And if we later spot true multicollinearity, we'll prune or combine these redundant features. And for the next visualization that we use, we just understood the prevalence of the risk factors using a proportion bar chart. So we observe that diet is present in 100% of at-risk cases, which is in red, and smoking is about 90%, and diabetes and alcohol consumption hover around 60 to 65, and the rest is in green. So what we will do is in logistic regression, we're going to ensure that these imbalances don't warp coefficient estimation, and in random forest, we will also apply balance weights so each tree sees a fair representation of risk versus no risk when choosing splits. Now for the last one, we use histograms for each binary predictor's overall frequency. So we observe that smoking and obesity occur in well over 60% of records, and family history and medication use are nearly 50-50, and some categories are rarer. So what we will do is, for logistic regression, we will consider dropping or merging truly rare categories. And for random forest, we will enforce constraints like a minimum leaf size or maximum tree depth to prevent splits on near constant features from loading the forest. So that's it for our EDA.
Now, moving on with the data training or data modeling. So in this project, we developed a machine learning model to predict a heart attack risk based on a variety of patient health indicators. So as we have seen earlier in the data pre-processing, it consists of many columns such as the age, sex, cholesterol, heart rate, diabetes status, family history, smoking, alcohol consumption habits, BMI, blood pressure readings, and other lifestyle and medical factors. We began selecting these features and relevant feature to define our target variable, which also indicates whether a patient is at risk of heart attack. So upon knowing that, we then split the dataset into training and testing sets by using an 80-20 ratio. So to ensure that the model performs regardless of scale differences among features, we applied min-max scaling to normalize each feature to a 0-1 range. So also take note, this specific model training that we use is a random forest with SMOTE or SMOT. So continuing, each column was scaled independently and the scalars were saved for later use during the prediction. So since our dataset is synthetic, we still consider the real world medical datasets that it often suffers from imbalance within the given dataset, and to lessen the imbalance of the actual patient records of heart attack risk, we applied SMOT, or synthetic minority oversampling technique, that is an algorithm to balance the training data by generating synthetic examples of the minority class. And then after that, again, we trained the data using a random forest classifier using the balanced training data. So after that, we ensured that the data is already balanced. We use random forest classifier to further train it. So to evaluate the model more reliably, we performed a 5-fold cross validation, which showed a strong average accuracy. So the model was then fitted on the full resample dataset, and we evaluated its performance on the original test set. We calculated the accuracy score and generated classification reports. So after validating the model, we then saved both the trained classifier and the individual feature scaler using a job lib, ensuring that this can be reused in future predictions. And then finally, we defined a custom prediction function that accepts a new patient's data as an input in the form of dictionary, scales it appropriately using the saved scalars, and ideally, and most importantly, it returns to the predicted heart attack risk. This function makes the model easy to integrate into healthcare tools or web-based application where real-time risk assessment is needed. So upon using the random forest classifier, it shows a 0.600, it results to a cross-validation accuracy of 0.7808, and for the accuracy, it is 0.6001. While this is not as high as was expected, it is still validated, and it is very hard to test the accuracy given that the data that we have is skewed. So with this, accuracy is not good, but it works. So the data works, like the data prediction works. And also this is the classification report as well. If you can see the precision, recall, F1 score, and support. So basically, this just means that and then you can see here the 0-1. So 0-1 is the result, like the labels, and it shows you how precise that the model actually predicts. So for 0, it is 0.65 or 65%, and then for 1, it is a little bit, not a little bit, but it is definitely significantly lower with 0.64. While the accuracy is not so bad with the 60%, it shows here that it is in the amount of precision that it predicts for both the heart attack risk and non-heart attack risk is very skewed or far from each other. So moving on to another modeling classifier that we did. So we did a little bit of logical regression. To make the model production ready, we saved both the trained logistic regression model and the individual scalars, again using the job lib, as we also did in the random forest. And then finally, a prediction function was also implemented, allowing new patient data as an input, again using a dictionary as what we did in the random forest, and it will be passed to the model to return to a prediction, so whether or not they are high risk or potential to heart risk disease. So the two model was used to provide more options and to test the accuracy result. So in the logical regression, So with the logical regression, it is the same application with the random forest one, but the main difference is we use random regression. So the process is still the same. So we split the data set into training and testing set with the 80-20 ratio. And then the next step that we did is compare or balance the data because the class is very imbalanced. So, which means that there are fewer individuals that are classified as high risk in comparison to those without risk. So, in random forest, we did this smooth, but here in the logical regression, we just indicated that the class weight is balanced so that it will automatically adjust the weight associated with each class to offset imbalance and to help also the model to focus on the minority class during the training. So the model was trained on the scale data and then evaluated on the test set. Next is we measured the model's performance using accuracy and a classification report as what have we also did in the random forest classifier. So the classification also provided detailed metrics such as the precision we call F1 score for each class. So we have an accuracy of 0.5031, which is 50%. So random forest classifier is much higher in terms of accuracy. And then for the classification report, again, for the 0 and 1, it shows the same result. As we have seen, we used two classifiers that are suitable, the top two most suitable for our data set. And the accuracy is still not high or not high enough to deem the model as accurate or credible. And also with the precision, with the 65% and 35% ratio, that's not a good number to begin with. And then which makes the model works, but the data that we have again is imbalanced, and there are a lot of factors that we need to take into account in terms of diagnosis, especially in the medical field. So that is all for the training and feature engineering.
Okay, so to show how we were able to create a user interface for our models, we used Streamlit, which is a platform that allows people to create user interfaces for their data science projects. So we just imported Streamlit over here in our Python script, and then we also made sure that we loaded the models over here so that we could have or load it here in our Python script for the UI script. So this is what we were able to do with that. So this application is hosted with Streamlit, and then we could also share this link to others, so it's not locally hosted. So this application shows what the app does and also shows what the models do in very simple language. Now, for the main part of this application, we would be able to input values of the patient and predict their likelihood of heart attack. So let's try to input values right now. So let's say these are the characteristics of a hypothetical patient that we have. Maybe they have 2 bottles, and then 90, then maybe just 2, and then maybe they do have diabetes, they have an unhealthy diet but normal stress levels, and then they don't have any family history of heart disease, and then for BMI, maybe they have 35, maybe not so good BMI, and then maybe they have 8 hours of a sedentary state every day, and then 120 for that, 80 for this. Maybe we could put 1 million here for annual income. Okay, let me check. All right. Then for triglycerides, you can keep it at that. And then for previous heart problems, they don't have any. Maybe just 3 days of activity per week. And then they do have medication, and then maybe they just sleep for around 6 hours. So we can predict that. Okay, so the model predicted, or the logistic regression model predicted, that they have high risk of heart attack. Now for random forest, let's see. Okay, for random forest with these same values, they have a low risk of heart attack. So that's how our user interface for the model works. Alright, so now that we've seen the end-to-end flow, let's look into why this pipeline matters. So it democratizes risk insight. So we wrap complex data, transformations, and model logic behind a simple UI. And this is where patients can enter their basic health metrics and immediately see an understandable risk score, which may help them engage proactively with their own care. And it also supports clinical decision making. So healthcare workers juggling heavy caseloads get a fast, consistent second opinion. Pipelines like these take messy health data and turn it into clear, trustworthy risk assessments that are scalable and can be further developed for potential real-world use. Thank you very much for listening.